SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 14, we will talk about groundwater yield. The different concepts that would be covered in this particular lecture will be on groundwater flow, Darcy's law, measurement of yield of an open well, and measurement of yield of other wells. So, when we talk about groundwater flow, we have already talked about permeability and we have already talked about groundwater yield in the earlier lectures. So, we would say that groundwater flow depends on hydraulic gradient and the characteristics of the aquifer. By characteristics of the aquifer, I mean permeability of the aquifer, and other things also play a role definitely. But when we talk about groundwater flow, these are the two primary criteria that has to be actually investigated. So, hydraulic gradient is basically whenever we have got an aquifer, like you can see in this particular image, this blue zone is this blue zone is this particular area where this is the blue is the aquifer, and you can see the level of the water table in this particular aquifer. So, the water table is more or less certain few meters below the surface from over here, and we can see that if we take a reference plane or maybe the impervious stratum below, or we can take just a a reference frame, we can see that H A is the height of water table at this particular point, and H B is the height of water table at this particular point from this particular reference plane. So, the difference between this height is basically the difference between this height, and then there is the distance between these two places. This is given by L. So, if I take H A minus H B and I divide by the distance L, then we get that is the difference in these two heights, that is delta H divided by L, and this is the known as the hydraulic gradient. So, or you can say this is the slope of this particular piezometric surface or this particular surface of the water table. So, this difference in height is what actually enables water to flow from one point to another. So, hydraulic gradient, so groundwater flow depends on this hydraulic gradient between these 2 points, and also the characteristics of the aquifer or the characteristics of this particular soil, and by characteristics we mean the permeability of this particular soil. Now, let us go through permeability. If you remember, permeability is the rate of flow of water through an aquifer of unit cross sectional area under unit hydraulic gradient at 15 degree centigrade temperature. Now, what it means is it is the flow of water through an aquifer, then that means water flows through the aquifer, and we take just a unit cross sectional area and under unit hydraulic gradient. So, if the hydraulic gradient is more, the rate of flow would be higher. That means the amount of the permeability is only defined for each for one, that means what we can say is permeability under unit hydraulic gradient we get a value, but obviously as you can understand, when the hydraulic gradient changes, the rate of flow will also change. So, permeability is the constant or the coefficient that we will use in our final model, and groundwater yield is equal to, we have also learned about this, that is, it is the quantity of water extracted by gravity drainage from a saturated water bearing stratum. So, that means this is already water is held inside this saturated water bearing stratum or this aquifer, and then we say that some amount of water will be retained within it and some amount of water will come out by normal gravity drainage. So, this water that will come out is basically the water that we can actually get. So, this is called the specific yield that for this particular soil. So, groundwater yield and permeability together, when we consider them both, based on this we can formulate, we know that we can formulate a relationship between the flow and then between the permeability as well as the hydraulic gradient of that particular place. Now, Darcy's law states that the flow of water through an aquifer is governed by Darcy's law, of course, and which states that the rate of flow, in this particular case the rate of laminar flow, and is directly proportional to the hydraulic gradient and the area of cross section of the soil. So, that means when we talked about hydraulic gradient, it was the change in the height, and then there was also, we have talked about permeability, which was for unit area. So, when we want to decide for a particular well, then the well has got a larger surface. So, we have to multiply with the overall area for this particular value. So, what we find is Q is proportional to S, which is the loss of head or hydraulic gradient. This is what Darcy's law state, and then it is also proportional to the cross sectional area of the soil. So, Q is equal to S and A. So, this is balanced using this coefficient K, which is nothing but the Darcy's coefficient of permeability. So, Q is equal to KSA, where Q is the flow of water in the soil, K is Darcy's coefficient of permeability, V is velocity of the underground water, and this velocity of underground water is basically the specific discharge velocity. That means the velocity at which the water is coming out of that particular well, and then A is the total area, and S is the slope of hydraulic gradient line, which is given by dH by dL. So, when we know the slope of the hydraulic gradient line and we know the total area, we can determine based on the permeability of the surrounding soil what would be the amount of yield from a particular well that we dig in a particular soil. So, in Darcy's law, if I substitute Q by A over here by V, which is Q is the total flow of water divided by area, that gives us velocity, and then we get V is equal to K into S, or V is equal to K into dH by dL. So, this is another relationship that we can also look into. So, velocity is also dependent on the hydraulic gradient. The more is the hydraulic gradient, the more would be the velocity of flow or the discharge velocity from that particular soil. Now, V is, as we are saying, even though we are calling it movement of water underground, it is basically the specific discharge velocity, which is different from the actual flow of water inside ground. So, its specific discharge is not the actual velocity of groundwater flow, and because flow actually is taking place inside the soil and there are a lot of pores in the soil. So, the water has to travel in between the pores, and it is not a straight path or a straightforward flow like that. So, in that sense the water has to travel a larger distance. So, actual groundwater flow velocity is basically 3 to 5 times the velocity of specific discharge or the specific discharge, right. So, actual groundwater flow velocity, that is Vp, is given by the discharge velocity divided by porosity of that particular soil. So, this rho is porosity and V is the discharge velocity into the well. So, this is basically when water comes out of an opening inside the well. So, that is the discharge velocity, and this Vp is the actual flow velocity within the soil. Now, there are certain empirical formulas which has also been derived through experiments, of course, to determine groundwater velocity inside soil, and one of those formula is the Hazen's formula, where V is given as equal to K dash dash into S into D10 whole square divided by 60 into 1.8 T plus 0.42. Now, what are these values? So, we can see that V is proportional to, so there is some effect of T, which is temperature. If you remember, we were saying that flow happens and permeability is there at 15 degrees centigrade. So, temperature plays a role. So, T is there, and then it also depends on S. S is nothing but the slope of the hydraulic gradient line, the same S, and D10 is basically the effective size of particles in aquifer in millimeter, and D10 signifies 10% of the particles will pass through this particular size. So, if I mention a size of a particular size of particles, at least 10% of the particles will be of that particular size. So, D10 is equal to effective size of particles in aquifer in millimeter. So, the size of the particle is also an indicator of porosity. So, porosity is being considered that and also and K dash is also that constant with approximate value of 1000. It is a constant which balances the other permeability constants and so on, and then S is the hydraulic gradient line, and then divided by 60 is there. So, overall this equation could be also used to determine velocity of flow inside the ground, and that unit is given in meter per day. Okay. So, now that we know how to determine the yield of groundwater, the next thing, and also we know that what is the velocity of flow of groundwater. So, we now can determine what sort of yield or what sort of water we can get from particular wells, and there are different kinds of wells. We talk about two kinds of wells over here. One is the dug well, which is a standard well that you see in many households, where you dig using maybe mechanical mills, but in most cases it is like a individual will actually human beings actually do the job. They keep on digging and they put on rings, and they actually you create a well at your backyard, and this is only possible when the groundwater table is at a pretty high level. And the other is tube wells. Tube wells could be also put up in certain buildings, means in certain real estate development projects, or maybe the municipality even can draw water using deep tube wells. And this both this kind of groundwater sources are used in urban areas and also rural and semi-rural areas, and we need to understand how much water could be drawn from these particular sources. So, this is something where we learn about the measurement of a open well yield. So, first we will learn about how to measure the yield from a dug well or a open well, and then we will learn about how to measure the yield from a tube well. So, how is this measurement done? And how do we measure that? There are different methods, of course, but first of all I would like to say the difference of head between the water level inside the well and outside the well will cause flow of water inside the well to meet the requirements of pumping. So, that means whenever you dig a hole in the ground or a well in this particular case, the water table in the surrounding soil and the water table inside the well would be at the same level. Now, if you start drawing water from the well either by means of a pump or by just using certain buckets or certain other containers, in that case the water level in the well goes down, and when it goes down, then what happens? The water level from the surrounding areas will try to water from the surrounding areas will try to enter into the well from the bottom of the well, right, because the well, it's an open well, and the difference in head causing the flow, that means the difference in hydraulic gradient between these particular two areas is known as the depression head. So, this is the difference between the water in the outside and the inside of the well, and this hydraulic gradient will also ensure that water will flow from the surroundings into the well. And Darcy's law states that velocity increases with increases in head. So, this is what we have derived in a few slides, 2 slides in the previous slide, and what we see is because the velocity of flow increases with the head. So, the more is the head difference, more is the flow, and accordingly what happens, the slope, the more is the velocity, means the slope of that particular whenever water flows inside this particular well. So, it is flowing from the surroundings, and usually what we see that the shape of the water table around the well takes the shape of a curved cone, and this is called the cone of depression. So, that means if I have a ground level and if I have got a well, and if I see that this is the water table in that particular area, so when we draw water, suppose the water level in the well is over here. So, definitely there is a difference in between the hydraulic gradient between the surroundings, right. So, we will see that this water table bends gradually, and this is where the water from the aquifer will start flowing inside the well and start entering inside the well, right. And so, this water table actually gets bended, and why this bend happens? Because the more is the hydraulic gradient, more would be the velocity, and more would be the velocity, more would be the bend. So, gradually the more you come near to the well, you will see a more bended surface. So, that is why this is known as the cone of depression. And then there are two methods how we can actually measure the yield of a well. These two methods are called the actual pumping method and the recuperating test method. So, the actual pumping method, it is pretty straightforward. That means the rate of pumping is adjusted using a variable pump maybe, so that it would be same as the rate of percolation. Rate of percolation means the amount of entry of water inside the well. So, that means we will adjust the rate of pumping so that it matches with the yield of the well, right. And we can say from the rating of the pump, we can determine what is the yield of the particular well. Or we can do something called a recuperating test method, where pumping is done and then stopped. So, after so that means there is some difference in the level of water, and then the rate of rise of water table is determined by calculating the quantity of water percolating inside the well. So, once we stop the pumping, that means there is some difference in the head, and then we see at what time the water will come up and how much water is going to come up, and we can measure that within that particular time, and based on that we can determine the yield of the particular well. So, just to show in a better figure, in this particular figure you can see that this is the well that has been drawn, this one, and then you can see the diameter of the well is 2r, and this is the static water table. So, this is the level of at where the water table is right now, and once the well starts drawing, when you start drawing water, then you see the water table gradually bending, and then this is from where the water will start entering, and this difference is known as the drawdown, which is big H. This is the height of the static water table, and the small h, which is the level of water after pumping. So, this is the difference, this is the drawdown, and this curve is known as the drawdown curve, and this overall cone is known as the cone of depression, and the cone of depression has got at the surface level of the water table, it is basically a circle. So, this circle of the base of the cone is known as the circle of influence. So, base of cone on the water table is called circle of influence. So, this has got a lot of implications, why I will tell you. So, what happens? So, suppose you have got a real estate project, like for example, there is a housing colony, and you have put in a deep tube well over here, and you are drawing water from here. Now, as soon as you are drawing water, the surrounding water table actually is bended, and during the time you are drawing water, or during the time water is entering into this particular well, the water table will be bent like this. Now, suppose these people are actually drawing water from depth of around 300 meters. So, it is a pretty big deep tube well. Now, you have got another building, maybe these people do not have so much resource. So, they have dug a tube well till maybe 100 200 meters. Now, what will happen when the water is active, when these people draw water, the water table has bended, and because the water table has bended, this area there will be no water to be drawn from this particular well, because it is in that particular zone, this particular well now falls in the zone where there is no water at all, because the water table has bended and it is actually not available, and this area's water is actually not, you would not be able to draw water from this particular area. So, this building will not be able to get any water. So, that is why we cannot have deep tube wells at very, very close proximity, and we really need to estimate the yield of a well to determine how much amount of drawdown and this will happen, and what kind of bending will take place in this particular water table, so that we can determine at what distances what kind of tube wells could be put in, and so on. So, this kind of some rules are already there, but that at certain you cannot have too many deep tube wells in one project. There has to be certain distance between the deep tube wells. So, some of these these are like 1.5 square kilometer per deep tubal. So this is the distance or spacing between deep tubals. You can say, so this is the command area of deep tubals, or you can say 120 hectares could be called the command area of the deep tubals. And discharge is around 45 liters per second in Indo-Gangetic plain. And what we have found that center to center between two deep tubals should be kept more than 600 meters. So if you keep that, then at least there is some safety, considering that the deep tubal is of standard nature. So this is how this phenomena of this drawdown happens, or this bending of the water table happens, and that actually is a big problem in urban areas. So in many we have seen that in many cities people have to find that the deep tubals have gone dry, and they have to again put in a new deep tubal which would be at a much higher depth to actually reach the groundwater. Now we will determine the yield of a well, or so before we determine the yield, there is of course specific yield or specific capacity of a well, and we actually determine it using the recuperating test in this particular example. And the test is conducted during summer to determine the dry weather yield, because of course in summer the yield is lower. So if we can determine the dry weather yield, of course we should be safe during the other seasons as well. So specific yield C-A can be defined as the volume of water released from storage by an unconfined aquifer. You remember what is an unconfined aquifer? Unconfined aquifer means there is no straight, it is not under pressure, that it's a open aquifer. That means there is no confine, it is not confined from the top, right? So it's an unconfined aquifer, and so specific yield can be defined as the volume of water released from storage by an unconfined aquifer per unit surface area of aquifer per unit decline of water table. So per unit decline of water table, that is the hydraulic gradient you can say, and per unit surface area of the aquifer. So that means from the aquifer, if you make a hole in the aquifer, and from per unit area of the aquifer, this is the amount of water that will come out, right, for one for per unit decline in water table. So per unit or per unit of hydraulic gradient, right. So this is what specific yield is. So as you can understand, if this is specific yield, so if I remove A, so if I multiply by A, so this would be area of the surface of the well, or the surface of the aquifer, through which water enters into the well. So in case of an open well, so we know that in case open wells are like this, there are at the surrounding there are rings, and you cannot draw water from the surroundings. Usually water enters from below. So in this case, the surface is is just the area of a circle of the of this particular diameter. So it is around pi r square. So pi r square is the area of the well, and using this area water will enter. So definitely when we have specific yield, if I multiply by pi r square, then we get the yield of the well, and also for unit hydraulic gradient. Now if I want to understand that, okay, it's for unit decline of water table, and if the unit decline of water table is even higher, then the yield would be even higher. So we will again multiply with whatever is the unit decline of water table, or in this case we call it a depression head. Okay. So in recuperating test, what we usually do is we will first pump, we will see at what level the water is, and then what we will do is we will see how much water will be there inside the well after a certain period of time, right? And then we determine what amount of water entered into the well, and from that we determine the yield of that well. So this is how this has been derived. So where C-A or specific yield, it could be defined, derived as 2.3 divided by T and log 10 log to the base 10 of S1 divided by S2. Now where T is basically the time after pumping was stopped, and this is given in hours. So obviously S1 and S2 are the depression head in the well, and the S1 is depression head in the well just after pumping was stopped. So this is the lower level, and S2 is the depression head after time T. So this is after a certain amount of rise has happened inside the well. So, C dash A is the specific yield, as you have this is constant depending on the soil through which the water enters into the well. So, this depends based on the surrounding soil, we get a value of C dash. And so, as we have seen that Q is equal to C dash, total yield is equal to the specific yield into the hydraulic gradient and also the area. So, specific yield is C dash A into S, and we can replace C dash A by 2.3 by T into log base to the base 10 S1 in S1 divided by S2, and this actually allows us to determine the yield of a well based on the recuperating test. So, instead of using Q is equal to C dash into A into S, we use C dash by 8, so that C dash, because we know already the value of C dash by A, and so we can put that in the equation. If A and S are known, we can determine the yield of the well, or Q. So, Q is the discharge or yield of the well in meter cube per hour, and S is the depression head of the well, and A is the cross sectional area of the well in meter square. So, cross sectional area of that particular well, because water enters through the below. So, let us see one problem. And so, during a recuperating test, the water level in an open well was depressed by pumping by 4 meters and is recuperated by an amount of 2.6 meters in 90 minutes. So, after 90 minutes, it was recuperated by an amount of 2.6 meters. So, that means the depression head is 4 meters minus 2.6 meters, right. So, the initial once the pumping was stopped, it was 4 meters below. So, after 90 minutes, it has gone higher by 2.6 meters. So, the depression head is 4 minus 2.6 meters. So, we need to determine the yield from a well of 2 meter diameter under a depression head of 2.8 meters. So, this is based on the first part. We have to determine the specific yield of the well. C dash A value could be determined, and once we determine the C dash A, we have to multiply with the depression head of that particular well and this diameter of area of that particular well, and we can get the yield. And similarly, we can also determine that to get a yield of certain value like 5 liters per second, how much should be and with a depression head of 2 meters, how much should be the diameter of that well. So, if I want this amount of water, what should be the diameter of the well that we should take? Let us see the solution. So, first we determine the specific yield C dash A, which is given by the formula which we just learned, and here S1 is initial drawdown 4 meter, S2 is final drawdown, which I said 4 minus 2.6 meters, and it will come to 1.4 meters, and then T equal to 90 minutes, which is 1.5 hours, right. So, C dash A is equal to 2.3 divided by 1.5 into log to the base 10 4 by 1.4, which comes to around 0.699 meter cube per hour. So, this is the specific yield of this particular well. Now, when we determine the yield of the well of a diameter of 2 meters and depression head of 2.8 meters. So, definitely we have to multiply the specific yield into the area cross section of the well into the depression head. So, cross section of the head, because it is 2 meter diameter, we have taken pi by d square by 4. So, this is the area, and into 2.8 is the depression head, which comes to around 1.71 liters per second. And if I want to have a yield of 5 liters per second, obviously I will have to have a bigger diameter. So, I can solve it in this way: 5 liters per second I convert first into meter cube per hour, which comes to around 18 meter cube per hour. I do that by multiplying with 60 into 60, seconds into minutes, and divided by 1000, because meters to liters, liters to meters has to be divided by 1000, and S2 value is 2 meters. So, Q is equal to, again, the same formula, where 18 is equal to 0.699. So, we already know the yield, we know the specific yield, we know the depression head. Only thing we need to know is the area of the well, and from that area we can calculate the diameter. So, area is 12.88 meters square, and using the same formula pi by 4 d square equal to 12.88, we can determine d equal to 4.05 meter. So, this is the diameter of the well required to get a yield of around 5 liters per second. So, now that we have learned about how to determine yield of an open well, where we have not talked too much about there in open wells are used by households, but for commercial purposes, like when the municipal corporation or the urban local body supplies you water, then they will use deep tubeels and all. So that is where we need to, and of course they will pump the water out, and pumping, when they pump the water out, usually it is in liters per minute, and so we need to determine the yield of in those kind of systems. That means how much water we can get from there. So to do that, we usually use Thiem's equilibrium formula, and this equilibrium formula is for different purposes. There are three variants of the formula. One is given for gravity wells, which are standard deep tubeels, and in where the water is not under pressure, so it is an open well, it's not a confined aquifer. And in the other cases, it could be a confined aquifer. So it's an artisan well, as we have discussed earlier, that artisan wells where you draw water from a confined aquifer, and then it is under pressure, and because it's a confined aquifer, it is under pressure. So with a little variant of this particular formula, we can use it for we can use it. So this is Thiem's equilibrium formula for pressure wells. Then there is Thiem's equilibrium formula for infiltration gallery, which there is again a variant in that particular case. Now, just before I go into explaining the formula, I will just how it was derived. Now, there are few terms that we are using. That is, first of all, it's equilibrium. Why equilibrium? The reason we call it equilibrium is because it is equilibrium because when pumping is being done from this particular well, we assume that the rate of percolation and the rate of pumping is stabilized. That means both are at equilibrium, and for that particular situation, what is the amount of water that what is the yield of that particular well that we will be able to determine. So that is why equilibrium is there. And also you have to understand, this is a deep tubewell, that it is put inside an aquifer, and we assume that that the entire aquifer's depth is being utilized by this deep tubewell, and this deep tubewell has got openings on the sides through which water enters into this particular pipe of this deep tubewell. So that means that instead of the lower part or the cross section of the well, more important is the surface area of this particular well. So surface area is basically the diameter of the 2 pi r circumference into the height. So this is the surface area of the well through which water comes in, right? So when Thiem derived this formula, what he did was, I will just go to the next page. In this particular case, what he did, for example, this is the main well, you can see over here, and two test wells were drawn, were actually dug at certain distances from this particular well. And then let us assume that this is test well 1 and test well 2, and then what it was done was, these are two observations wells which were within the circle of influence of the main well. So that means whenever you pump from this water, the water table will go down, and within that circle of influence we will have two test wells. And as per Darcy's law, we know that flow through any concentric cylindrical section Q is equal to Kia. This is gone here. So this is again that gradient area, and this coefficient, and where I is the hydraulic gradient, and because we are using this concentric cylindrical sections, we can assume that I is equal to dH by dr. So dH and dr is basically the height of water table observed in that particular observation well when you draw water from this particular well. So in this particular case, and dr is the radius of that well. So if we assume a well which is of radius from of size this size, then obviously this is the radius of the well, and it will, because it is on the same drawdown curve, it will have the same circle of influence, right? So using that, we can say that gradient is basically dH by dr, and h is the height of the cone of depression at distance r, which is radius. So based on this, we can say that, and a, as we just told you, that a is equal to 2 pi r into h, and so q will be 2 pi r h into k, this coefficient, into dH by dr, which is the gradient. Okay. So dH by dr is the gradient. So we can also take this in a different form, which is dr by r is equal to 2 pi kh into dH by q into dH divided by the entire thing divided by q. So, this we just shift q this side and we take dr on the other side and r on the other side. So, if we do that, we get this. Now, if we integrate between the limits r1 and r2 and h1 and h2 and h2 are the heights of water table in these two test wells, and r1 and r2 are the radius of this two test well. Then when we do that, we get a particular equation which could be we can work on that, and once the final form of that equation is this one, where q is equal to pi into rho into k divided by 2.3 into h square minus big H square minus small h square divided by log to the base 10 r big R by divided by small r, and this q is in meter cube per day. Now, what are these values? Now, what we can say, km is the transmission, I will come to that. H is the static head or the height of top of the water table for the impervious stratum or aquifer depth. So, that means this is the impervious stratum. We assume that the entire aquifer is being utilized by this particular tube well, and this is the static head or the water table. So, this is that, this entire distance is basically the big H. So, this is the aquifer depth or this height of the top of the water table from impervious stratum or the end of the aquifer. Small h is the height or depth of the water in the well just after pumping. So, this is the height or depth of the water just after pumping, maybe the height of water is until this. So, this is the small h. And r is the radius of the well, and big R is the radius of circle of influence, the for this entire this one. So, this is the big R, this radius of influence big R, and rho is porosity or fineness of the soil, k is the constant or soil permeability, which is same in all direction. So, these are some of the assumptions when this formula was derived, like it has to be equilibrium, the soil has to have same permeability in all directions, and there has to be the test wells are there, and then once we do that, this rho this pi into rho into k divided by 2.3, this again from meter cube today, if I convert into liters per minute, I multiply by 1000 and divide by 24 into 6 this 64 over here, and then we can convert all this into km, and this so this was in meter cube per day, and this is liter, so this is 60, sorry, and so this km value actually is basically this entire part is taken inside km. Okay. So, km is called the transmission constant of the aquifer. So, so if I can derive km, if I know km and if I know h square, which is the static head or the height of that particular aquifer, and then if I know h square, which is the height or depth of water table after pumping, and then if I know the circle of influence and the radius of that particular this particular well, then we can derive the total yield of that particular well. So, the new thing that comes over here is this circle of influence. If I know yield, then we can also determine circle of influence as well. Now, let us look into one problem. I think this we have already discussed. So, in this particular problem, you can see that the following observations were made on a 40 centimeter dia tube well. So, this tube well diameter is 40 centimeter. So, this is 20 centimeter. So, of course, it is not representative, means it is not exactly proportional, but let us assume the main well is 20 centimeter of radius. So, rate of pumping is equal to 2000 liters per minute for this particular well. What was observed was drawdown in the test well 20 meters away, it was observed as 2 meters, that is 20 meters away is the first well, this is over here. So, this is the radius of that particular. If we assume that this entire well, this is a concentric area around this particular well. So, this entire area is a concentric circle, and this is another concentric circle. So, this one is of small r, this is 1 r, and then this radius of influence, which would be somewhere around here, this is the large R. And so, drawdown in another test well 40 meters away, which is 40 meters away, this is 1.4 meters. So, here it was 2 meters drawdown was observed, and over here 1.4 meter drawdown was observed. So, depth of water in the well before pumping was 30 meters. So, that means this is the static height of the water table. So, this is 30 meters. So, what we need to determine? We need to determine the radius of the circle of influence. That means, if I know the radius of circle of influence, I can determine what distance should be the next tube well, right? And that means we can also determine how what kind of urban planning or building norms that we have to put in to prevent the next building to actually their deep tubules will run dry if they are somewhere in between this radius of influence. So, we have to take care of that. And so, we need to determine the radius of circle of influence, we need to determine the transmission constant of the aquifer or Km value, and then we need to determine the maximum rate of discharge from this particular well that is possible. So, right now we are drawing water at 2000 liters per minute, but we want to understand what is the maximum rate at which we can draw water. So, using Thiem's formula, which is Q equal to Km into h square minus small h square divided by log to the base 10 big R by small r, this is given in liters per minute. What we can do is, we consider this first well, and here we can say, if I put in the values for this particular from the values that we have given earlier, Q equal to Km into 30 square, which is big H, which is the static head, and then 28 square is the, because 2 meter drawdown was observed. So, 28 square is small h. So, 30 minus 2 is 28, and then log to the base 10 r by 20. Big why 20? Because we assume a concentric. So, this is the radius which is 20 up till this. So, we assume a concentric well of 40 meters diameter or 20 meters radius, whatever. Similarly, for test well 2, we assume the second well, which is in the same way we consider, but here we take 40 and the drawdown is 28.6. So, the height after pumping is 28.6 meters because of 1.4 meters of drawdown, and this 40 meter is the radius. So, now this is the second concentric well or circle that we can take. Now, because these are of the same well, they are in the same within the same drawdown curve, we can assume both of them would be same. We can equate both of them, and what we see that we can, when we equate both of them, the yield will be same in both the wells. So, Km into this particular, the first, this one, this value yield is equal to same as this yield, and then we can solve it like this, where 30 square minus 28 square divided by 30 square minus 28.6 square equal to log to the base 10 r by 20 log to the base 10 r by 40. Now, we can solve it, simplify it further. This comes to around, once you solve it, it comes to around 1.414 and equal to log to the base 10 r by 20 and log to the base 10 r by 40. Now, again we can write log 10 r by 20 as log 10 log to the base 10 r minus log to the base 10 20, and then log 10 r minus log 10 40. So, when we do that, we can actually now solve it. When we solve it, we get this particular equation, from where we get log to the base 10 r is equal to 2.328, and from there we can determine the value of r, which is 212.8 meter. So, 212.8 meter is the circle of influence for this well. So, any other well, if you dug within this 212 meters, it is certainly going to be affected by the pumping of this particular well. So, at least the next well should be somewhere beyond 212 meters, or it could be somewhere in between as well, but you have to adjust the rate of pumping for that well or the timing of pumping to determine the amount of water that you can draw from both these wells. So, this is how we can determine the circle of influence for a particular well. Now, based on that, we can now determine Km value, because we already know that this particular observation of drawdown happened because of a discharge of 2000 liters per minute. So, when we put that in that equation, we can, and all the other values we have got, like 30 square minus 28 square, and this is r, big R, and this is small r, and this was the first well, the first observation well, you can say. And when we equate that, we get the value of Km as this, which we can solve, and we can get it as 17.70. So, this is the transmission constant of this particular aquifer. Now, the final question we have asked is, what is the maximum discharge of the well? Now, maximum discharge of the well occurs when H is equal to 0. So, obviously, in this particular equation, when will Q be maximum? When the value of H squared would be less. So, that actually is, it's not, it's a theoretical value, it's the maximum discharge is a theoretical value. That means, when the level of water is at the almost at the same, there is no drawdown as such, right. So, over here what we can say is, when H value is equal to 0, if I put it in the equation, we can see that this can be Q max is equal to 17.7 into 30 square divided by log 10 to the base 10, 212.8 divided by 0.2, because if you remember, our radius was 20 centimeter, and then Q max equal to 5.26 meter cube per minute. So, this is the value that we can get from this particular equation, or sorry, if it not meter cube, I think we have to solve it for liters per minute in the same way over here. Okay. So, we will we need to adjust for that particular value, or it could be, I have to check this, it is either 5.26 meter cube per minute, or we can give it in liters per minute as well. So, to conclude, the flow of water through an aquifer is governed by Darcy's law, that is what we have learned. So, we have also learned how to determine the yield of a particular open well as well as a deep tube well, and we have seen that actual groundwater flow velocity is higher than specific discharge velocity, that is something what we have learned as well, and a minimum spacing has to be maintained between the two deep tubules and so that none of the deep tubules are affected by each other. So, these are the different things that we have learned from this particular lecture. These are the references you can study, and thank you.